Okay, so I wanted to pick up where we left off last time. Um, and so you probably recall that when last we met, we had used the Bohr model of the hydrogen atom to determine the ground state energy and the energy of each of the successive allowed energy levels, slowly increasing up to a value of zero. Remember that they're all negative because we're uh, talking about a bound system. Um, this had, and we alluded to this last time, a couple uh, of major triumphs for Bohr. Um, First, that he was able to theoretically explain the already observed binding energy of the electron in the hydrogen atom, 13.6 electron volts, and he was able to explain qualitatively and to to a very great extent quantitatively the uh, the allowed or observed wavelengths uh, of emitted light when hydrogen gas was heated up. So um, the so-called Lyman series, the Balmer series, the Paschen series, and the Brackett series. So you'll also recall from last time, uh, and I guess before I do that, I should also point to where I took the original image. Um, they're not responsible for kind of the added in stuff, so any errors there are mine. Um, you'll recall last time that we determined the the energy level in the Bohr hydrogen atom as such uh, that ultimately it went as either minus k charge of the electron squared over twice radius divided by n squared, where n is some integer, positive integer, or it's minus the mass of the electron times the electric field constant squared times the charge of the electron to the fourth divided by I twice h bar squared, and then that divided by I n squared again, where n is a positive integer. And again, remember that this looked like minus 13.606 electron volts over n squared. We can use this to to rederive the Lyman-Balmer Paschen and Brackett series by saying that uh, the transition from a higher state to a lower state emits electromagnetic radiation, uh, and the energy of that photon has to be the difference between those two energy levels. You can solve this for frequency, um, such that frequency goes as the initial energy level minus the later energy level divided by h, Planck's constant. And since we already know what the equation for E is, we can plug that in and say it's plus ke squared over 2a naught h times quantity 1 over n final squared minus 1 over n initial squared end quantity. Hopefully that's not terrible. We also have the statement that the speed of light c is equal to frequency times wavelength. And so we can say frequency relates, or we can say that 1 over the wavelength is the frequency over c, which is just this over c, right? The difference between this and this is just the addition of dividing by c. This gives us the familiar Rydberg constant, which also allows us to determine what the wavelengths of each of these series is. So for the Lyman series, your for the Lyman series, you're just dropping down to n equals 1. For the Balmer series, you're just dropping down to n final equals 2, and so on and so forth. The Rydberg constant is just this prefactor, ke squared over 2a naught hc. And if you plug in values in the SIMKS set, you'll get that it's about 1.097 times 10 to the minus 7 inverse meters. Now, Bohr took this model and all of its successes and applied it to other atoms too. Other atoms where the atom has been ionized such that it only has 1 electron. So the idea here is you don't have in the Bohr model, you don't want to have to worry about electrons interacting with other electrons. You just want it to worry, or just want it to interact with the nucleus. And so in this Bohr model, the difference between what we had last time and what we have this time is this, that the radius is the Bohr radius times n squared, but divided by z, where z is the number of protons in the nucleus. It also takes the energy levels that we had previously and multiplies by z squared, where again z is the number of protons in the nucleus. So it's a decent first pass model, but it fails in many respects. As spectroscopy was improved, there were a couple of drawbacks even for hydrogen, but more specifically for this extended Bohr model. First, within improved spectroscopy, it was shown that some of the lines that you see that look like single lines are really multiple lines that are just very, very, very close together. And that isn't explained simply in the Bohr model. Additionally, you see some Zeeman splitting where upon application of magnetic field, a single line might be split into 3 separate lines that are all closely neighboring each other. So 3 distinct wavelengths, as with the application of a magnetic field. And again, the Bohr model can't explain that. So we're going to need a fully quantum model to explain what's going on there. But I do want to get us to a point where we can start to discuss that stuff. And so let's look at the correspondence principle. I want you to keep this in the back of your mind as you go through the remaining stuff this semester. And we had a version of this in relativity as well, right? But the basic idea is that classical physics worked really well for a really long time. And so quantum physics should agree with classical physics if the difference between quantized levels becomes small. So, um, so in the event that the discrete levels start to get close enough that they can be approximated as continuous, quantum physics should start to look a lot like classical physics. That's what this means. So hopefully that's all right. Okay, so let's get into some of the truly revolutionary parts of quantum physics. Um, and so I guess I I'm starting in in a more uh, classical model where we could say that total energy is the kinetic energy term plus the potential energy term. The kinetic energy term is just half mv squared. X dot is just the first derivative of x with respect to time. So half mv squared is half mx dot squared plus v. We could say that because we believe in energy conservation, that uh, the the first derivative with respect to time of energy should be zero because energy is constant. So d dt of this stuff, right, yields that 0 is 2 times half is 1 m x dot times x double dot, where x double dot is just the second derivative of x with respect to time, plus dv dx times x dot. In other words, this would be dv dx times dx dt, right? Hopefully you can convince yourself that that's a fair statement. Um, so I've written it out here for you. Um, dv dt would just be dv dx dx dt, right? And that's what this is, dv dx times x dot, but x dot is just dx dt. Note that we can factor out an x dot from this and say that 0 is equal to x dot times quantity mx double dot plus dv dx. Note that there are two possible solutions that would make this go to 0. One is if x dot is equal to 0, and that is typically what you expect in an engineering statics class. So something that a civil engineer might take, right? Typically there you don't want buildings to move. Um, the parenthetical part of this, that mx double dot plus dv dx is equal to 0 solution, that's what we mean by dynamics. And so so here, and this is what we'll be spending probably a fair fraction of the remainder of our semester on, I'll ask you to remember Newton's second law, that um, you could write it a few different ways, but one of the ways you could write it um, is that the the derivative of the potential with respect to x is minus the force. And we'll use that now as we consider a simple harmonic oscillator. So here, the spring potential is just half kx squared, and so the force is minus kx, right? The derivative of this with respect to x would be 2 over 2 times kx, and then negated is f, so minus kx. And so we can plug into this equation and say that 0 is mx double dot plus kx. So 0 is equal to x double dot plus k over m times x. That's just dividing through by m, right? And so we could write this as I x double dot plus the square of the square root of k over m times x. And we could just define omega to be the square root of k over m, in which case we get x double dot plus omega squared x. You probably remember from physics 130 that we could write an equation for this as x of t is equal to a sine omega t plus b cosine omega t. We'll come back and remind ourselves of this again in a few minutes. If we apply boundary conditions to this equation, let's insist that x is equal to 0 when t is equal to 0, and that x is equal to some maximum value x naught at t equals pi over 2 omega. In which case we get that x of t is equal to x naught sine omega t, and x dot of t is just equal to omega x naught cosine omega t. In other words, the first derivative with respect to time of this equation is this equation. The first derivative with respect to time of this equation is this equation. So we also have our statement that total energy is the kinetic term plus the potential term. And so plugging in what we mean by x of t and x dot of t into this equation, we get the following. Half mx naught squared omega squared cosine squared omega t plus half kx naught squared sine squared omega t. Note that since we have cosine squared plus sine squared, actually that's we're able to simplify this as half kx naught squared, because remember omega is radical k over m, so omega squared is k over m. So k over m times m is just k, and we get half kx naught squared times quantity cosine squared omega t plus sine squared omega t, and quantity is half kx naught squared. We also could have converted this k such that we could have written this as half m omega squared x naught squared. All this tells us is that the energy is constant, and it's equal to the energy when it's all potential or the energy when it's all kinetic, right? Either of those is a fine statement. We also could look at expectation values. So the expectation value of sine squared theta is the expectation value of cosine squared theta is half. And so we could say that the expectation of the kinetic energy or the expectation value of the potential energy is just the total energy over 2. And so now we're going to put all this back together, and we could look at what we mean by expectation values of x squared, of momentum, which is just mx dot, or of a momentum squared. First thing is remember that if you disturb a mass on a spring in equilibrium from equilibrium, it will just oscillate back and forth about the equilibrium point, and so the expectation value of x is 0. Similarly, it will spend just as much time moving in the plus direction as the minus direction, and so the expectation value of momentum is also 0. Coming back to this statement, we could say that E over 2 is k is half m x dot squared is half m x dot squared I expectation value. We could do the same thing for the potential energy term, and it's half k times the expectation value of x squared. What we glean from this is that E over 2 is half m times the expectation value of x dot squared. So the halves cancel, and we get that E is equal to m times the expectation value of x dot squared. Or that m E is equal to the expectation value of p squared, right? If I multiply both sides by m, I have m times E on the left, and I have m squared times x dot squared expectation value, but that is what we mean by the expectation value of p squared, right? Similarly, we could take the second equation up here and say that E over 2 is half k times the expectation value of x squared. The halves cancel again, and we get that E is just equal to k times the expectation value of x squared, or that E over k is equal to the expectation value of x squared. All right, so now we are making some headway. We want to look at delta p times delta x. And we could write this as the square root of the expectation value of p squared minus the expectation value of p quantity squared. And the expectation and delta x we could write as the square root of the expectation value of x squared minus the expectation value of x quantity squared. But we already said that the expectation value of p and the expectation value of x were both 0, right? That was this statement. And we said that the expectation value of p squared is equal to me. The expectation value of x squared was just e over k. Multiplying these things together, we get e times the square root of m over k, which we could also write as e divided by the square root of k over m. But we already defined k over m as omega. And so what we're seeing here is that there is a relationship that we can draw for delta p delta x. And what we'll find as we move forwards in quantum mechanics is that this value is actually subject to a lower limit, and we'll derive what's known as the uncertainty principle in quantum mechanics from a similar argument. So, but that's just a reminder of classical physics. So, in quantum mechanics, we're going to define the momentum operator as h bar over I times d dx. and we'll let x go as x. Okay, so now let's turn to the Schrodinger equation. And I'm not going to derive this for you. In fact, um, you don't see derivations of the Schrodinger equation. You see justifications of the Schrodinger equation. Sometimes they get called derivations, um, but the Schrodinger equation is more empirical than anything. So um, justifications, yes, but but derivations are a little trickier. So okay, so with that said, the one-dimensional, and we're going to work in one dimension almost exclusively. We'll do a little bit of atomic physics, in which case we'll need to look at 3 dimensions. But at least while we're getting our feet under us, we're going to mostly deal with 1D physics. So the one-dimensional time-dependent Schrodinger equation, is minus h bar squared over 2m times the second partial derivative of psi with respect to x plus the potential energy function multiplied by psi is equal to ih bar times the partial derivative of psi with respect to t. This doesn't always have to be true, but we are going to restrict ourselves to only worrying about separable equations where psi of x and t can be broken into a purely spatial component and a purely time component. We're going to restrict ourselves to these because these are challenging enough. So this does allow us to break this into the one-dimensional time-independent Schrodinger equation, the 1DTs, right? Time-independent Schrodinger equation, where we're looking at the separable solutions. So in this case, the version of the Schrodinger equation that we will spend much more time on is this one, minus h bar squared over 2m times d squared psi of x dx squared, that's the second partial derivative with respect to x of psi of x, plus v of x times psi of x is equal to e psi of x. And let's turn to the first kind of celebrated problem here, and it's the one-dimensional PIB problem, the one-dimensional particle in a box. And so in this case, what you have is there is a region between 0 and L where the potential energy goes to 0. Let me pause here for a moment and fix this. Unpaused. The potential energy goes to 0 between 0 and L, but it tends towards infinity anywhere else. I got ahead of myself and also included this energy term because I'm going to plot them both on the same axes. But for now, I want you to think of this as describing potential. So hopefully that's okay. There's a couple of things I want to point out. Since v of x approaches infinity in regions 1 and 3, there's no way that you can find the particle there because it would have to have an energy greater than V, right? Greater than or equal to. And that would assume infinite energy, which is not a physical solution. The other thing I want to point out here is in this Schrodinger equation, psi of x, and actually psi squared of x, psi star psi, um, is related to the probability of finding the particle in some region of space. And so, since we can't find the particle, there's zero probability of finding the particle in region 1 or region 3. Psi of x in region 1 and psi of x in region 3 both must equal 0. In region 2, the nice thing that happens is the potential goes to 0. And so in region 2, this Schrodinger equation, the time-independent Schrodinger equation version, this term is gone because V is 0. And so what we have is minus h bar squared over 2m d squared psi dx squared is equal to e psi. So we can write this as d squared psi dx squared is equal to minus 2me over h bar squared psi. Now, we've seen this equation just moments ago, in fact. It's this equation, right? 0 is equal to the second derivative with respect to time of x times some plus omega squared times x. But if I brought one of these terms to the other side of the equal sign, I would have x double dot is equal to minus omega squared x. And we said that the solutions to those took on the form a sine omega t plus b cosine omega t. Well, we have some intuition then that a good trial solution here would be psi of x is equal to a sine kx plus b cos kx, where k is just the square root of I 2me over h bar squared. So if we try this, let's see what happens. The second derivative of psi with respect to x is minus k squared times quantity a sine kx plus b cos kx end quantity, but that's just equal to minus k squared psi, right? That tells us that k squared needs to equal 2me over h bar squared, or again that k is just equal to the square root of 2me over h bar squared. We could write out a more general statement for psi as it's 0 if x is less than 0, right? That's in region 1. It's also 0 if x is greater than L, that's in region 3. But in region 2, it takes on this value a sine of kx plus b cosine kx. Yay. We can go further than this. We can insist on the continuity of psi at x equals 0. In other words, the probability of finding psi can't be discontinuous, right? And so if psi squared, psi star psi really is related to the likelihood of finding the particle in some region of space, then it can't be 0 here and some really, really non-zero value in region 2, right? Across this boundary between regions 1 and 2, it has to be continuity of psi. And so we can say psi of 0 in region 1 needs to equal psi of 0 in region 2, but we already know that psi of 0 in region 1 is 0, and so we can say that 0 has to equal psi in region 2 at x equals 0. If we plug that in, we get 0 is equal to a sine of 0 plus b cosine of 0. Well, the nice thing there is sine of 0 is 0, right? And cosine of 0 is 1. And so this really just becomes 0 is equal to 0 plus b. That tells me that b has to equal 0. In other words, we could just cross out this term in our psi of x function. In other words, psi of x in region 2 just has to be a sine kx. Hooray. Okay, then let's also look for continuity of x at x equals to L. It goes to 0 in region 1, but it also goes to 0 in region 3. And so in region 2, it also needs to approach 0 as it approaches 0 or approaches L. So if we look for continuity of psi of x at x equals to L, psi of region 3 of L is equal to 0, and that also means that psi of region 2 at x equals L also needs to equal 0. So we have that 0 is equal to a sine radical 2me over h bar squared, which is k, times L, end quantity, right? There's a couple ways this could turn out. We could let a be equal to 0. That would absolutely satisfy this. The problem with that is, again, if a is equal to 0 and b is equal to 0, then all three of these are 0. And so psi is equal to 0 if x is less than 0, psi is equal to 0 if x is greater than L, and psi is equal to 0 if it's between 0 and L. That, since psi star psi squared, is related to the probability of finding the particle, that would mean the probability of finding the particle is 0 everywhere. And so that's not the physical solution if we know there really is a particle. The other way of making this go to 0 is insisting that that sine of the stuff in parentheses is 0. Well, that will be 0 anytime this stuff in parentheses is equal to n times pi, right? Remember, n is an integer times pi, sine goes to 0 for any of those. And so we could say that this stuff in parentheses, radical 2me over h bar squared times L, the L isn't in parentheses, is equal to n times pi, where n is some integer. We could square both sides, and we get 2me over h bar squared times L squared is equal to n squared pi squared, in which case, solving for e, we get that it's equal to n squared pi squared h bar squared over 2ml squared. This is kind of interesting, right? This tells us that the energy is quantized, right? Because n is some integer value. Yay? N is 1, 2, 3, 4, so on and so forth. Psi in region 2 is a sine of radical 2me over h bar squared times x, but we just solve for e, so if we plug that in, n squared pi squared h bar squared over 2ml squared in for e. Note that the m's cancel, the h bar squareds cancel, the 2's cancel, and what we're left with is 2 pi squared over L squared under the radical, n pi, well, let me try again, n squared pi squared over L squared under the radical, which is just n pi over L times x. And so now we have this statement for psi, right? It's 0 if x is less than 0. it's 0 if x is greater than L, and for x between 0 and L, it's equal to a sine quantity n pi x over L. But again, if what we mean by psi squared is the probability of finding the particle, well, the particle has to be somewhere. And so we need that if we add up all of the probabilities, psi star psi dx is, so the probability of finding the particle in some region of space dx is just psi star psi dx. If we add up all of those probabilities over all of space, it has to equal 100%, right? It has to give unity as a result. And so this is our normalization criterion. The particle is somewhere. And so if the expectation value of psi squared is I is the probability of finding the particle in a region of space, then uh, then that has to represent unity if you look over all space. And so we can plug that in, right? From minus infinity to infinity of psi star psi dx. Well, I'm going to break this into 3 regions from minus infinity to 0, where psi is 0, and so psi times psi star psi. So psi star is the complex conjugate. Take all the the i's and turn them into minus i's. This is pretty easy because uh, it's in trig functions, so you don't have to worry about uh, the complex components. We'll do some examples where you do have to worry about complex stuff, but we'll worry about that not today. So this first piece is just looking at the region of space where region 1 and psi is 0 there. This is looking at region 2, and so we just said that psi in region 2 is a sine of n pi x over L. So squared, a squared, sine squared, n pi x over L dx. From 0 to L are my limits, right? That's the second region. And then we also have to worry about from L to infinity, again, where psi 3 is also 0. So the first term, the last term, those both add up to 0. I'd like this to be a constant, so a squared can just come out of the integral. And so what we get is the integral of sine squared n pi x over L dx. We already said that sine squared, the expectation value is half. So from 0 to L, this is just L over 2, right? That was way back here, I think. Yeah, right. Um, so this term is just going to be a squared times L over 2, right? The limit from 0 to L of half L over 2 times a squared. But if we really do insist that this is equal to 1, then a squared times L over 2 has to equal 1. We can solve that for a. A is just equal to radical 2 over L. And so we can come back here and say that psi of x is equal to 0 when x is less than 0. It's equal to 0 when x is greater than L. But when x is between 0 and L, it's going to take on this normalized wave function value of radical 2 over L times sine of n pi x over L. The energy of these levels is n squared pi squared h bar squared over 2ml squared. Okay, so let's look at the results that we've just acquired. So this would be our n equals 1 state. So note that the wave function psi goes to 0 at x equals 0 and x equals L. and it's at its maximum halfway in the middle of our box. Let's look at the n equals 2 state, the first excited state. So the wave function for this would look like so. Again, it goes to 0 at x equals 0 and x equals L. But also know that this one goes to 0 directly in the middle of the box. We'll talk about that in a second. Let's look at the n equals 3 case. The second excited state, the n equals 3 state, again goes to 0 at x equals 0 and x equals L. This time has two additional points where the amplitude goes to 0. Let's finally look at the n equals 4 state. I'm going to do this because if I do more than this, we're going to run out of space. Again, goes to 0, x equals 0, x equals L, has the 3 nodes in the middle. That's interesting, but perhaps the more physically meaningful thing is the psi star psi, the complex conjugate of psi multiplied by psi. But in this case, that's just psi squared. So this time the n equals 1 case, again, has peak value right in the middle and goes to 0 at the two edges. Let's look at the n equals 2 case, the first excited case. Again, what I wanted to point out is that remember that psi star psi, the square of psi, represents the probability of finding the particle. And so this tells us that the most likely place to find n equals 1 is right in the middle. You're not going to find it at the ends. Let's look at the n equals 2 case, because I think this is where you start to see interesting stuff. This time, again, not going to find it at the edges. You're going to find this about halfway through the first half of the box or halfway through the second half of the box. The interesting thing here is there is 0 probability of finding this particle in the middle of the box in the second excited state. So, sorry, in first excited state, n equals 2 case, but first excited, right? This particle will not be found in that state in the middle of the box. It's most likely to be found at the center of either the first or second half, right? That's where the amplitude goes to max value. Let's look at the n equals 3 case, the second excited state. For this one, it is most likely to be found at the center of the first third, the second third, or the third third of the box. And it will not be found exactly 1/3 of the way across or exactly 2/3 of the way across. Right. Lastly, let's look at the n equals 4 case, which is the third excited state. This one is likely to be found at the center of the first fourth of the box, the center of the second fourth of the box, the center of the third fourth of the box, or the center of the fourth fourth of the box. But it will not be found 1/4, 1/2, or 3/4 of the way across the box. And lastly, let me sketch this in a way that is a little, I couldn't do all of this in one plot, but note that this first one that we examined is the plot of psi against x. The second one is the plot of psi squared against x. This last one that I want to examine is what happens if we place these in terms of energy. And so the first thing I want to point out is the lowest energy this particle can have, just by virtue of being placed in the box, is not zero, right? Just by putting it in the box, confining it to the box, it has some 0 point energy of pi squared h bar squared over 2ml squared, right? The first excited case, the n equals 2 state, has 4 times as much energy, right? Um, and so it is 4 times higher up on this plot. The third one, the n equals 3 case, the second excited state, has 9 times the ground state energy. And the fourth one, the n equals 4 case, has 16 times as much energy as the ground state energy, n equals 1 case. Now, again, I want to make sure that I'm stressing that if I'm actually plotting psi, each of these psi values has to go to 0 at x equals 0 and x equals L. This is more of a way of kind of showing you that each of these states exists at a different energy associated with the equation that we solved for up here. Now, the the interesting feature that I want to stress here is just by confining this particle to the box, we have guaranteed that it cannot have 0 energy. It has to have energy of at least pi squared h bar squared over 2ml squared. And it has quantized energy values such that it must have some integer squared multiple of this ground state energy. All right, um, that is our 1D particle in a box, and also our Rydberg discussion. I'm going uh, to use this as both our Monday and Tuesday lecture because I suspect that this is more than you can probably absorb in one lecture. Um, so as always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your day, but not so much that I don't see you on Tuesday or Wednesday.